Okay. Hello, everyone. Um, yeah. So last Tuesday, I had an emergent meeting, so I uploaded the video to give you some idea how we can program on GPU, right? So today, let's continue to learn something about the GPU or CUDA programming. Let me share the slides. So because I assume some of you may not have the time to, go through the videos, let's just quickly recall the idea or the the contents I have taught in Tuesday. So the general idea is that how we can utilize the high or extremely high parallelism in GPU to realize the parallel programming, right? And at the beginning, I introduced the idea why the GPU has a very high parallelism, because the GPU architecture is designed specifically for the throughput, and the CPU is designed especially for the low latency, okay? And that gives some idea about the different specification or architecture specifications on the CPU and GPU. So you can notice that the GPU has a very high parallelism with a high number of the threads, and also with a high throughput for the memory bandwidth. Okay, so that's some feature for the GPU. So if in the future you consider if your program or your application is mostly memory bounded, so you should consider to use a GPU to realize your high performance program. Okay, and later we introduce some SIMD and the program with the CPU SIMD and GPU SIMD. Okay. Right, this is just the development history of GPU. Okay, then this is a very important thing you need to remember, even in the future, when people are talking about, okay, how we can use a GPU to program, what is a basic framework. For example, if you want to go to the NVIDIA or AMD, most of the development tasks there are based on the GPU. So you need to understand what is the 7 steps you can develop a GPU code, right? Because the GPU is still the accelerator, we need to control the GPU computation by CPU. So as I mentioned last lecture, you need to first set up something on CPU, set up something on GPU, and copy the data from CPU to GPU, and perform the GPU kernel, and finally copy the data back from GPU to CPU. Okay, so we really refer host as a CPU, right? And device as GPU. So host, device, or GPU and CPU. So you should understand the concepts clearly. Okay, and the first step, just try to emphasize this part again, because this is really, really important. Sometimes I observe the students or my PhD students cannot get the correct results. The reason is that they just forgot to initialize the memory space for GPU, right? You just copy some data, but the GPU compiler may not report the error. So you just don't initialize anything on the GPU, but still you can perform the kernel or anything, and you cannot return the correct answer. So this 7 step is really important, okay? And later we realize our first GPU program, the vector addition. I think I have already done a demo, but I can do another demo today about how we can separate the GPU code into the different parts, okay? But the general idea is that you have a large array, right? And the array has a different elements with different indices, right? And the general idea is that you should use different GPU threads to perform on the different elements in the array, right? This is just a general idea. And later we will notice that if the array is really, really large, right, it's exists the number of the threads you can use on GPU. So what should we do? So the idea is just you don't have enough threads, but you have a very large array. How you should do? The idea is just to use one thread to perform on several elements. Is that right? So, but currently, because we assume that the number of the thread is enough, we don't have a very large array. So we just ask each thread to work on each index. Okay, but later you will see something different. And this is how we calculate the index for GPU. So later I will talk about the CUDA programming model. So, but generally speaking, for the different kernel, you can launch different number of the threads, and each thread would have its own thread ID, similar to MPI, right? You launch, for example, 1024 processes, and the rank ID would be from 0 to 1023. Okay, so each process will have its own ID. Similarly to GPU, each thread will have their own thread ID. So how I can calculate the thread ID? We will have some formula, but general idea is we have a different thread block, and each thread block will have some threads, and we use the block ID times the number of the threads in the block plus the thread ID. You will calculate that, the index for the threads. Okay, so this is also something I would show later, but general idea is to give you some impression how we can program using the CUDA. Okay, so this is first code. So maybe considering some of you may not have time to look at the video, let's just to redo the demo. Okay, so can you see the screen? So the terminal, okay, now I'm in the terminal of our cluster. As I mentioned, you can use the cluster, but it's better to use the Alabama Supercomputer Authority, their cluster, because they have much more GPU here. But if you want to do some quick demonstration, of course, you can use our GPU. So let's see the first GPU code I showed last lecture. Okay, so this is the first GPU code. So this is a GPU kernel. This is the most important thing you want to run on the GPU. Okay, so far it's very simple. It's just to ask each GPU thread to calculate the C elements resulting calculate the result of C based on the A and B arrays. Okay, and the main function is still the same. It's like a C or C++ code, but please follow the 7 steps. You first need to allocate the memory for the host, then allocate the memory for GPU, okay? And then you initialize the data on the GPU or CPU host, right? Because you want to have some real data to calculate, and then copy the data to device, okay? And then you set up the number of threads and the number of threads per block and how many thread block. Okay, so this is something I will mention later, but assume you have a bunch of threads here, you just execute the kernel. Okay, so the kernel, this is just a syntax for how to launch the kernel. This is a number of threads per block. This is how many blocks, thread blocks. Okay, and then you pass the pointers to the kernel. And after calculation, you just copy the data back. Similar to memory allocation, right? You need to give the CUDA memory copy the idea how many bytes you want to copy, right? Similar to CPU memory copy. And finally, you just freeze the memory on both CPU and GPU. Oh, this is a very simple kernel, but maybe if I ask you to program that, it's not so easy. Even if you know the scheme, you should spend some time to tune or to debug, because this is your first, similar to Hello World, right? This is your first code. And to compile the code is just very simple. You just use NVCC. So NVCC, you can think about it's a wrapper for NVIDIA compiler, okay? And it's based on the GCC or CLAN, depends on your compiler tool chain. So we can compile this code. Okay, but because this is on the head node, you cannot, you can try to run this code, but definitely it will return you some error, right? The result is not correct. As I mentioned, the correct result should be 1. So that means, can you see, even if I don't have a GPU on your laptop or your server, whatever, it can still give you the result. It doesn't report any error. So that means this is a silent corruption of your kernel, but it doesn't report any error, right? It cannot successfully call the kernel. So that's the one thing you have to be very careful. Sometimes CUDA code cannot give you the correct result, but you still cannot observe any error reported in the program, right? Not segmentation fault, not, you just return some incorrect result, right? If we SH to the GPU node, if we try to rerun, you can see that because we have the GPU device, right? And we can correct get the answer. But both of the, the executions do not report any error here, right? So this is something I really want to emphasize here. If you would do your final project and you find, okay, I get something, but please verify the correctness of your code. So as the first lecture of this semester, I mentioned that when you calculate the two matrix multiplication, you have to verify the final result if it's correct. But at that time, maybe you don't feel it's very important, right? Because just a CPU code, it's okay. But if you perform some GPU code, you call some kernel, maybe the kernel would crash or just exit silently, right? You don't know anything wrong happened here. So please make sure the final result would be correct, okay, in your final project. Compare your GPU result with your CPU result. This is a very important thing here, okay? So this is our first demo. So I will show how we can, so now you can see everything is in .cu file, right? We have some main function here. We have some kernel here. We have some head file here, but of course, if you want to develop a large project, you cannot put all of the function in one .cu file, right? So I will show you how we should develop separate files, including host code and device code, and compile them together, okay? So let's go back to the slides. Let's go back to the slides. And yes, today we will continue with the CUDA programming model. So I just spent 10 minutes to give you some a recall, or just let's recall some idea, right? And now let's see what is the detail for the CUDA programming model. So CUDA is a programming model designed for heterogeneous architectures. It has a wide SIMD parallelism architecture for NVIDIA GPU, and it can scale up your program or speed up your program very well if your code has a good scalability here. But because CUDA is developed by NVIDIA, so it's only can be used for NVIDIA GPU, right? This is a this is a commercial product. So if you have any other AMD or Intel GPU, cannot use CUDA. So this is a limitation for CUDA. But also it's a good thing because the NVIDIA spend a lot of time, efforts to optimize the CUDA programming model. So usually if you have a good code with CUDA, you can achieve a very good performance. As I mentioned in last lecture, so for example, we still have other heterogeneous programming model, for example, OpenCL, right? OpenCL can also use for different GPU architecture. But the problem is that sometimes if you test the same piece of the code for CUDA and OpenCL, CUDA usually have a better performance or higher performance than the OpenCL implementation. Because this is just a simple idea. If you want to have the generality, right, you should sacrifice some performance. But if you want to have a very high performance, then your code may be specifically tuned for some architecture, right? So this is just the trade-off. But today, because the CUDA GPU or NVIDIA GPU is widely used in the industry, in a computing center, no matter in Google or Amazon or somewhere else. So it should be easily to run your CUDA code in different computer system. Okay, and the CUDA can provide a thread abstraction to deal with the SIMD and the synchronization and data sharing between small thread groups. So that means a small thread of groups doing computation and the synchronization. Okay, so later we will see that we have the 32 threads wrap up together as a warp. We call it a warp. And these 32 threads need to execute the same piece of the instructions. If they cannot execute the same piece of the instructions, there would be some bad thing happen. Okay, so think about CUDA to do the synchronization or data sharing or the computation with a small thread of the groups. And that thread needs to execute exactly the same piece of the code or instructions. If you have some if branch, so I will talk about some detail later, but if you have some if branch, some threads go this way, some threads go that path, right? That will introduce a very bad performance to your code. Okay, but I will talk about that later. And the CUDA programs are written in C or C++ with minimum extensions, and you can separate your CUDA code into .cu or .cuh files. I will show you a demo, but the general idea is that it's similar to C++ code, right? You have the .c++ or .c HPP file, right? You should separate your CUDA code also into the different functions and header files. We compile use NVCC, NVIDIA compiler for CUDA to create objectives, okay, or object files, okay. So OpenCL is inspired by CUDA, but hardware software vendor neutral. So just as mentioned, OpenCL, so NVIDIA also has its own implementation of OpenCL. So just as I mentioned, every vendor follows the standard of OpenCL. Similar to MPI, right? So as I mentioned, so we usually in the class we use OpenMPI or MPICH, right? But different vendors have their different implementation. For example, Intel has their Intel MPI. Cray have their Cray MPI. They have their own MPI implemented and optimized for their system. Okay, similar to OpenCL, right? Every vendors have their implementation, but I believe NVIDIA put most of their efforts on CUDA. So their OpenCL code usually will have a low performance than CUDA. So you can easily download the OpenCL code and the CUDA code from any repositories and simply test on your CUDA GPU. You can observe that, or NVIDIA GPU, you can observe that. Okay, and for NVCC and G++, this is something you need to pay attention to. So CUDA is simply an extension of other bits of the code you write. So you can have both C++, HPP file and CU file and the CUH file. Okay, and you should use the NVCC to produce the objective file for the CU and CUH file. Okay, and since CUDA 7 to 9, there is a support by NVCC for most of the C++ 11 and C++ 14 language features, but you should make sure to read the restriction for device code. Okay, so they adopt some features for the CPP 11, CPP 14, but something, if there can be used, you should check the NVIDIA website. Okay. So there is no difference from how you link .o files from normal C++ code. So I will show you a demo now. Okay, so maybe it's a little bit small. Let's try to enlarge. So this is so first you can see that we have the different files, CUDA test.cuh file, original original CPU head file, and let's say this way. Okay, so this is a device head file. This is a host head file. This is a device function. This is a host function. Okay, so usually you can separate your whole program or projects into the different pieces because now you have host and device, right? Originally you have the CPU functions called the main function, and then you have some other function and some head files similar to device. Okay. So let me quickly show you how I don't want to show these slides because a little bit confused. Let me show you my example code. Okay, so this is the original code I just ran, right? I put everything in the same .cu file, and you can use MVCC to compile to run, okay? So what about, let's just separate this code into the device and the host. Is that I think this is a good idea because then we can know that how we can debug if the problem is in the host or in the device, right? So let's go to the, sorry, it's a little bit noise. Let's close the door. Okay, so if you look at the this repository, not repository, this folder, I separate the device code and the host code. Okay, so this is host code. I just, it's a really simple, right? I just put the vector addition wrapper here, okay? So if you don't know this is a GPU code, then yeah, it's just a normal CPU code, right? It's very simple. This is a simple CPU code. And then we put anything else for the host code into the .cu file. Okay, you can see here, this is a kernel, right? And this is a vector addition wrapper here, right? We follow the 7 steps, and here we call the external code, we call the GPU kernel, okay? And then we also have the vector addition head file. This is a device head file, right? So now we have the 3 files: main function, device code, and device head file. Okay, how we should compile them? This is the question, right? How we can compile them and how we can link them. So first, you should still compile the host code here, device code here, right? But you shouldn't generate the executable file because this is a objective file, okay? Object file. Oh, sorry, I should compile on the login node. Okay, yeah, this is a good thing for you to remember. If you're in the cluster, you should compile everything in the login node. Okay, so this is a login node. So we first compile the device code. So after that, you will know just that we have generated this file, right? This is a objective file. And then let's compile the main function. This is a host code, right? So you should use GCC because this is just as a C program, right? You should compile. Okay, so after that, you will generate the objective file for the main function, right? For the host function. The final step is to link them together, right? To link them together. So I should write a makefile, but because I want to break down how the makefile would work, so you can see the step by step. You first compile the host code, compile the device code, and finally you link all the objectives together, okay? And you can see that we use the MVCC and to link them together. You can also use a G++ to link them together. Both could work. So you can see here, you should put the dynamic library because you want to use the CUDA and CUDA. This is a runtime library, okay? And this is what you generated for the objective file, right? And this is the executable file, okay? I think you should be able to use a G++ as well. Okay, because this is just a linker, right? No matter you use a MVCC or G++, it should work. But remember that we use just use a GCC to compile the host code, and we use MVCC to compile the device code, and we use no matter GCC, the G++ or MVCC to link them together. Okay, so you can see after that we generate the executable. We just generate executable, and let's try to run it. Okay, we just try to run it. Okay, the result is correct. So, so this is just a general idea how you separate your CUDA or GPU project, right? You should put every kernel in the .cu file or wrapper, something here, right? But put your CPU code here. Okay, so something I can also play with, for example, I can put the data generation or initialization in the main function, right? I don't want to put everything in the wrapper here. I can, for example, I can put some malloc, this malloc back to the main function, right? Because this is just the CPU host code. And we can also put this code in the host, right? Let's see if there's any student has any question. Okay, sure. Yeah, I can definitely post this code on the Blackboard. Definitely, I will upload the original .cu file. I can upload this separate host and the device code, right? You can look into the code. And this is something you must look into. Otherwise, I don't think you can implement your matrix application CUDA code, right? But anyway, I mean, if you are lazy, you don't want to separate the code, it's okay. You can just put everything here, right? But I think it's more clear if you separate the code, the device code and the host code into the different files here. Okay, so if you have any question, yeah, just feel free to ask here. I think it's good someone asked the question. I assume you can automate this compilation process with Makefile. Yes, that's I just mentioned that, yes, I can do that with a Makefile. And the reason I don't do that because I want to show step by step how you should do something with the host and the device compilation. But definitely you can use the Makefile to automate this procedure, okay? Okay, so this is any question before I move on? Because some of you may, I mean, I know some of CS students would like to see the code better than to think about the architecture thing of that. It's a little bit complicated to know the architecture. I know that, yes, but it's important to understand the GPU architecture, and this is our first example code. Okay, both of them are very important. So I will upload the code to the Blackboard, and you can easily test. Okay, and also a good thing is that before you perform your final or do your final project, you should make sure this GPU code can be run on your system, right? This is also very important to test your GPU environment. But I believe in the Alabama Supercomputer Authority, their environment is very professional and production. You should be able easily to run the code on the cluster, okay? And if you have any questions, send me an email or send the staff an email. Okay, so let's continue. let's continue with our lecture. So I don't want to go to these slides because I have already let you know that how you separate the code with the different pieces, right? And after that, you can execute the code. Okay, so this is a very important part I want to emphasize here. So what is a GPU programming model, right? So how you can program the CUDA code and what is the general architecture to map your code into the architecture. So there is some keywords you must understand to code in CUDA. So first is the thread. As I mentioned, so you have a large amount or large number of the threads when you launch a kernel, right? And for the different thread within one thread block, you would have the thread ID here. So thread ID, what is X mean? Some students maybe ask, what is X mean? So X means that later you will see that thread, we can have 1D or 2D or 3D threads. For example, if you are simulate some problem in the 3D space, you don't want to convert each thread ID back to 1D case, right? You would like to have 3D coordinates, similar to MPI, right? As I mentioned before, MPI also have the 3D, 2D different coordinates. Similar idea, yeah. I think that this is a good idea to think about everything you cannot understand, just think about if there is any relation with MPI. So similar to CUDA, so if we launch a 1D thread block, then you only need to calculate the index of the thread based on the IDX. But if you have the 2D, you need to involve the thread ID Y. Or if you have 3D, you need to involve thread ID Z, okay? And also we have some block. What is a block? Concept of block. Block is that we define a group of the 1 to 512 threads. But I think now you should double check. Now it could allow you to run 1024 threads per block. So here, we call it block, or maybe some people will call it thread block, okay? Thread block, because this is the block for threads. You group a number of threads into a block, okay? And the grid is what? Grid is the number of the thread blocks. So there are three layers or architectures, right? So hierarchies, I should say hierarchies. So first is the threads, right? And the number of threads grouped together into the thread block or block, right? And the number of the block grouped together into grid. And when you launch execution, you can specify how many grids and what is the grid, what is the thread block. And totally, you should have the number of the thread blocks times threads per block to calculate the total number of the threads, okay? So I will give some detail later, but here are some threads you should, here are some concepts you should understand. And also, here is the architecture of the CUDA GPU, okay? So you launch the thread with in the block and the block within the grid, and the grid would execute on the different processing unit, shared the same global memory and constant memory and some memory. I'll give some detail later, but here are the three layers, okay? Threads, block, and grid. So this is a thread organization. You may think about the thread organization as an array of thread indexes. Yes, you just have the different levels of the thread organization, and you can use that to calculate the thread indexes. Okay, so each thread has its own programming counter, variable, register, process state, etc. No implication about how threads are scheduled. So actually, there is something deep thing too about how thread would scheduled by the CUDA. But I think from programming model level, you don't need to understand how thread, how blocks, how grid would be scheduled by the architecture. Okay, there is some scheduler here. Thread block is a parallel task. All blocks in kernel have the same entry point, but may execute any code they want. And the thread grid of kernel must be independent task, program valid any interleaving of the block execution. So what does this mean? So thread grid, for example, if you look at, let me show this code. Okay, so you can see here, when we call a kernel, for example, this kernel is a vector addition, right? You specify how many blocks for one grid, right? And how many threads per block. And each block can perform on different data, right? So there are about, different thread blocks would execute on different data blocks. And then there would be a parallelism, but they should execute the same kernel here, right? They call the same kernel. But what about a grid? So here we only have a one grid. One grid consists, one grid containing blocks, right? So here is how many blocks. For example, I assume we have 100 blocks here. So when you launch the kernel, 100 blocks would be executed on the GPU with the different regions of the data, okay? And each block would have, for example, 512 threads within each thread block. But this is only for one grid, am I right? It's only for one grid. One grid had 100 blocks. But if you want to have another grid with another kernel, you should perform another execution, right? So here is the point is that the grid is for the different kernel, and the thread blocks and thread is for one kernel, okay? So here is a point. So all the blocks in the kernels, all the thread blocks in the kernel have the same entry point, execute the same kernel, okay? But they may execute the different codes or different data they want. But the thread grid of the kernel must be independent task. Programming can be interleaved across blocks executions, okay? But usually we don't need to think about too much about how you want to do with the grid. Usually we will, every time we launch a one grid with a one kernel, you just configure how many threads and in one block and how many thread blocks in one grid. Okay, so parallel kernels composed of many threads. All the threads execute the same sequential program. Okay, so threads are grouped into thread block. So this is just some repeating. I just mentioned that, right? You group the threads into the different thread block, and each thread block will perform the same piece of the tasks. Okay, so after we know the thread, block, and the grid concept, and we know that where is the parallelism from the CUDA programming. So we have the thread parallelism. As I mentioned, each thread is an independent thread of execution. For example, as I mentioned, 32 thread would be grouped into a one warp. So one warp with 32 threads would execute on the different elements of the array, right? But the problem is that if this 32 thread encounter some if and else branch, for example, how I should say, for example, I can write something here. Oh, sorry. Okay, so I can run something here. For example, if the thread index, right, is smaller than 16, let's do C thread index is equal to A thread index plus B thread index. Else, it would do C thread index is equal to A thread index time B thread index. Okay, so I can write some code like this way, right? Right, I can write the code like this way. But the problem is that, for example, as I mentioned, you group some threads into a warp. This warp usually have the 32 threads. But if the first 16 or first half of the threads execute the plus addition operation, and the next 16 thread would execute a multiplication operation, that means this warp would execute on two totally different instructions, right? Because the first 16 would execute this instruction, but the next 16 thread would execute this instruction. And for the GPU programming, this is a very bad thing because it would make this warp to execute in sequential. Okay, so the first 16 threads would first execute the addition, and another 16 threads just wait there. And then the next 16 threads would execute a multiplication, and the first 16 thread would wait there. So that means if your warp or 32 thread may have some divergence within the warp execution. So here is my quick explanation. You need to pay attention that there is some thread parallelism here, but you should make sure that within each warp, so this is a warp, okay? I will give the concept later. So warp is every 32 thread grouped together, okay? So you can think about that for each thread block, there are, for example, 1024 threads, and the 1024 thread would be divided into 16, right? Warps. Not 16, 32, right? 32 warps. So that means each warp needs to execute exactly the same piece of the instructions. Otherwise, this warp will be divergent. Okay, so this is a thread parallelism, and also it's a data parallelism. So across the thread in a block, the thread could execute on different data, and across the blocks in a kernel, different block can execute on the different data, right? This is a data parallelism. And also there is a task parallelism. The different blocks are totally independent, and the independent kernel executing on the separate streams. Okay. So for the, I think this is something similar to the MPI programming. For MPI programming or the OpenMP programming, you have thread parallelism, you have data parallelism, also you have the task parallelism, right? This is some general things here. Maybe I should start the presentation mode. Okay, so for many parallelizable problems involving arrays, it's useful to think about the multi-dimensional array. So as I mentioned, if you want to simulate something, some structure, for example, if you want to perform a stencil, right? So as our project as an example, you want to simulate a stencil. So for stencil computation, if you have already done something for your project, right? The time step, that dimension has a dependency, okay? We cannot use any multi-threading or SIMD to do that. But for each 2D space, you definitely can use some SIMD or OpenMP or multi-threading, right? Similar, CUDA is also here. And you can define the 2D thread or 3D thread for the different scenario, okay? And how can we define the different dimension of the thread? So for example, DIM3 is a struct to define your grid and block dimensions. So if you look at the sample code, DIM3 grid 128, 128. So you define a grid of 128 times 128 times 1 blocks. If you define the thread block as 888, you will get a block of 8 times 8 times 8 threads. But still, you need to know how many threads, right? Even if multi-dimensional, right? It's a 512 threads within each block. So you can define any dimension you want. You can define as 881. It's just like a 64 thread, right? And then if you define the different dimension, when you want to calculate the thread ID, you should be careful. Okay, so as I mentioned here, you can see the thread ID, it has a 2 dimension, dimension X, dimension Y. When you want to calculate the thread ID for 1 dimension, I'm not sure if I have code here, but okay, but if you look at the previous code, how you calculate the dimension here, you can see the thread index is equal to block ID X plus block dimension X plus thread ID X. This is just a 1D, right? This is a block ID. This is a how many block, right? And the plus the thread ID. So, but if it's a 2D, then you should have the thread ID X, thread ID Y to get the thread ID X and Y. And use the X and Y to perform on the 2D array, right? For example, I can write thread index X is equal to this, and thread index, maybe I should write something here, okay? So for example, you can define thread index X is equal to block ID X, X plus times block dimension X plus thread ID X, X, right? But you can also define the thread index Y is equal to block ID X, Y times block dimension Y plus thread ID X, Y. Okay, so after you have these 2 IDs, you can ask, for example, thread index X. If I have the 2D array, I want to do the matrix addition, right? I can do something like this way, right? Index Y is equal to, I just copy and paste, is equal to this, oops. Is equal to this plus A plus B, okay? So you will have the 2D thread ID and use the 2D to perform on the 2D data, right? It's much easier to convert every index to 1D array and then to perform, maybe for example, if you don't want to use a 2D array for C, you just convert it into a 1D scenario, but you need to do the index conversion. So that would be very, complicated, right? So this is the meaning why you want to do 3D struct to define your grid and block dimension. Okay, when you launch the kernel, you just put the grid size and the block size here. Okay, and then this is your device code. Okay, and yeah, this is just what I just mentioned that, right? So you can have the 2D block. You can see here we have a 1 0 0 0 1 0 2 0 0 1 1 1 2 1. We have 6 blocks, right? You can define as a 2 times 3 blocks for the grid. Okay, and within each block you will have a 3 times 2. Okay, and you can use this grid block threads to work on one data region. Okay, and for this data region, you can also map into the 3D case. So this is just like you want to simulate something, right? And you block down the data and you block down the threads, you try to map them together. Okay, this is just a general idea. Okay, and what is a modern GPU architecture look like? So this is some famous figure for the GPU architecture. In the future, if someone show you this figure, you should definitely immediately to realize this is a GPU. So here, you can see SM. What is SM? SS means streaming multiprocessors. So for each streaming multiprocessors, there are a bunch of the CUDA GPU core, like a CPU core, right? Within each SMs. okay? And the different SMs shared the L2 cache. And each SM, it has its own L3 cache, okay? And all the GPU cache and the memory, so you can see here, they connect through the to the high bandwidth memory too. So this is the GPU memory, okay? So this is the GPU cache, and this is the GPU streaming multiprocessor, and within each streaming multiprocessor, there are a bunch of the GPU CUDA core, okay? Like a CPU core here. And there is an NVLink to copy the data from the GPU memory to CPU memory. As I mentioned, you should have the CUDA memory copy CPU to GPU or host to device, device to host. So the data would be copied from the memory here through the NVLink to the GPU. And this NVLink is connected between CPU and GPU. This is just a GPU card visualization figure, okay? And for each streaming multiprocessor, as I mentioned, there are a bunch of the GPU CUDA cores here, okay? And they share our L1 cache across the different CPU CUDA cores here. And they also have some register file, whatever. So this is some complicated architecture details I don't want to talk about here, but the general idea is that why we want to have a streaming multiprocessor. The idea is that each thread block would be mapped into one SMs. So for example, V100 GPU, there are 86 streaming multiprocessor. That means this 86 streaming multiprocessor can execute the different blocks or threads simultaneously, right? And for each SM, they share some shared memory and cache. So for example, if you launch a one thread block on one streaming multiprocessor, all the thread could share some shared memory here. So I will talk about what is shared memory, but you should know that the general, the memory architecture of the CPU and the GPU are quite similar, but in some details, they are totally different, right? The high level idea is that they have the memory, they have the L1 cache, L2 cache, they have the register, they have the different CPU or GPU cores, but how they group the cores together and schedule the call to execute are totally different. Okay, so here is a new concept, is streaming multiprocessor. Okay, so this is some simple figure. So you have the streaming multiprocessor 1 to n, and each processor just has a register file and shared memory, and they connected the GPU memory to device memory. Okay. Yes, we don't need to think about these things now. I will give some detail later, but the general idea is that there are a bunch of the streaming multiprocessor and a bunch of the CUDA cores within each streaming multiprocessor. Okay. So let's see if we want to continue the. Okay. So let's just finish these several slides and we can end it today. And think of the device memory. We also refer it as a global memory as a RAM for the GPU. So I just explained that, right? So this device memory is similar to the CPU memory. We usually call it a global memory. So still remember, I mentioned that the GPU has a much higher memory bandwidth compared to CPU. So this memory bandwidth means move the data from the global memory or device memory between the GPU memory and the GPU CUDA core. Okay, it has a very high memory bandwidth. For example, V100 GPU has about 1 terabytes of the GPU of the bandwidth, of the memory bandwidth. That means if you move the data from global memory to the CUDA core, it could have a very high throughput. But even if the GPU global memory has a very high throughput, it doesn't mean we don't need to optimize anything, right? It doesn't mean you just put the data in the device memory and use that. It will achieve a good performance. You can achieve a good performance compared to CPU, but maybe you use a GPU only achieve a 10 or 20 speed up. This is not very good because the GPU has a very high parallelism. So for example, you can use a high performance, you can use a high efficient GPU code to achieve maybe more than 50 times or 100 times compared to your CPU code. Okay, so how we can achieve such high improvement or the speed up? The problem is that you cannot only use the device memory here. So as we mentioned, this is a global memory. There is another concept is a shared memory. So what is a shared memory? So here is a shared memory. All the CPU, all the CUDA core are shared or can access to this shared memory. And there is a piece of the global memory here. So that means you think about L1 cache or L2 cache or register blocking, right? If you have some data that need to be repeatedly used, you should put the data in the shared memory. And the shared memory usually have, I think, more than 2 or 3 terabytes per second throughput. So that's a really large or high throughput. So that means if you only use the data stored in shared memory and you don't need to move the data from global memory to the shared memory, then your program will have a very good performance. Okay, so this is some global memory, but I just want to talk about more about the shared memory. Okay, and GPU have some streaming multiprocessor, as I mentioned. Each streaming multiprocessor has multiple processors, CUDA core, but only one instruction unit. So each thread shares programming counter. And the groups of processors must run exactly the same set of instructions at any given time with a single SM. So this is the architectural explanation of the warp divergence, right? So as I mentioned before, 32 threads has to run on the same set of the instruction. Otherwise, the first 16 threads would wait for the next 16 threads, right? The root cause or root reason is that these processors must run exactly the same set of the instruction at any time, given a single SM. So this is the root cause or fundamental explanation. So they cannot execute the different set of the instruction at a given time. They can only execute the same instruction. So that's why this is a very specific architecture for SIMD, same instruction, multiple data, right? Even if for your CPU, different cores can totally run different instructions, right? Even if you use the SIMD, that doesn't mean that a different core cannot run different instructions. But for GPU, this is a must. You must run the same piece of the instruction on the same SM. Otherwise, your code will have some divergence, right? You first run this piece and then run another piece. Okay, so while kernel is called, the task is divided into the threads. Each thread handles a small portion of the given task. And the threads are divided into grid and block. This is what I have already mentioned. There's some repeated content here, okay? So however, we will often only work with a one-dimension grids and blocks. So as a vector addition, 1D is definitely enough. But as I mentioned, if we want to do something for matrix or tensor or other higher dimensional spatial case, right? So maybe you need to use 2D or 3D. And the maximum number of threads per block usually is 512 or 100 or 1024, depending on the machine. But now I think the V100 has a 1024 threads per block you can use. Okay, and the maximum number of blocks per grid is 65,535. Okay, so can someone let me know how many threads you can use for each grid? So the maximum number of threads per block is, let's assume is 1024, and the maximum number of the blocks per grid is 65,000, right? So how many threads you can use for one grid or for one kernel? It's just a simple mathematical calculation, right? You just use 1024 times 65,000, right? Yes, you have the 67 millions of the threads per block. But the problem is that If you have some, for example, yeah, this is a good thing that, yeah, some students have calculated the maximum number of threads you can use here. But the question is that if I have a number of points more than these threads, right? How should I do? There is some data, you don't have enough threads. That means you should divide your loop or divide your data into the several pieces, right? And each thread run on different or multiple data points. So if you still remember, in this case, we don't care about the size of A and B and C, right? We don't care about that. But this is may raise some problem because we run on small data set and a small number of threads. But if you run the maximum number of the threads, but your data is larger than number of the thread, right? That means you have to write a loop here, right? For each index, it will execute index and the index plus something, right? For example, if I have a maximum number of threads of 1,000, but I have the 2,000 points, and then each thread need to run on 2 data points, right? And then you should run on C index and C index plus 1,000, right? Is that true? So here is a thing I just want to remind you, because the maximum number of the threads on the GPU has some limit, okay? So you cannot just launch as many threads as possible. It has a maximum, okay, or limitation. So if you go over either of the numbers on GPU, will give output garbage data, okay? And much of GPU programming is dealing with this kind of hardware limitation, get used to it. And this limitation also means that your kernel must compensate for the fact that you may not have enough thread to individually allocate to your data points, as I mentioned here. Okay, so some students ask a question. So if you have this point, should you try to divide it into half or just do the first in the set and the last point in the second set? I think this is a good question. So for example, if you have such as 671,078 for 1 point, right? And in my opinion, you should divide this point into half, but you shouldn't launch the maximum number of the threads, right? You can launch, for example, 40 millions or 440,000 something threads, right? And you can divide the point into half. It's not necessary to launch the maximum number of the threads, right? How many threads you can launch depends on you. You don't need to launch such a large number of the threads. You can launch less threads and partition your data points into half, and each thread would execute on 2 points. That would make your execution more balanced, right? So this is a point, and it doesn't mean that you launch more threads and you can get a higher performance. It's not this way, because even if you launch less threads, and for each thread they would finish their task sooner than you launch more threads, right? So that means you can still get a good performance, but how many threads to use? This is a very good question. I cannot answer you now because it depends on the different application. For example, if you are doing the matrix application, it's a good way to tune how many threads per block and how many blocks per grid. For example, if I ask you to calculate a 10 to 10 matrix application, and for example, usually you would use a 512 or 1024 threads per block. This is something fixed, but how many blocks you should use, it's good to tune. You can set up some default thing and try to play with the number of the blocks per grid. So that means that you should write a program that can adapt to different number of blocks. So if you, this is a very good question. Okay, so if you look back, you can see here how many blocks we are using here. It depends on how many threads you are using here. And for example, the maximum block count is array size divided by the number of the blocks right? So for example, in your case, how many threads you can use here? So for example, you have such a large of the points, and for example, you have a 1024, but it's still not enough. And then you should ask each thread to perform multiple points, right? But your program needs to adapt to different number of the threads per block and blocks, right? Then you can tune it gradually, right, to get a better performance. So my point is that you should put the number of threads, count, and number of blocks connected with the data size, right? And you can easily change or modify how many threads you want to use here, okay? Yeah, do I still have time? Yeah, I still have some time, but so here, each block is assigned. Let's just finish these 2 slides. Okay, so each block is assigned to a 1 SM, as I mentioned. So each SM needs to run each block, and each SM only can be run with the same piece of the instruction. Otherwise, they have to introduce some penalty. And inside the SM, the block is divided into warps, okay? So I have already introduced warps, but here it's better to understand warp concept again. A warp consists of 32 threads, as I mentioned, and this is a CUDA defined constant. So no matter which version of the GPU device you are using, warp is always 32 threads. So this is a really important concept for warp. People are usually talk about, oh, your code have some divergence, then it's on the warp level, right? So each 32 threads must run the exactly same set of the instruction at the same time, okay? Due to the fact there is only 1 instruction unit. And the warp run concurrently in a SM. So for example, we have 512 threads for each block, assume, okay? And that means we can have the 16 warps, right? And each time 1 warp running on 1 streaming multiprocessor, okay? This is the assumption. And how can you schedule all the 16 warps to run concurrently in 1 SM? So this is something GPU architecture helps you to do that. Okay, let me try to repeat that. So for example, we have 500 threads per block, okay, per thread block, okay. In the future, if I mention block, it's thread block, okay. And totally, we will have 512 divided by 32 is to 16 warps, okay. And each time, 1 warp is executed, I should say, is scheduled to execute on 1 SM. Okay, so that means the 16 warps can run concurrently on 1 streaming multiprocessor. How to schedule these 16 warps? So there is something called SM scheduler. Okay, so for each streaming multiprocessor, it has its own scheduler to schedule how you can execute these 16 warps. Okay, this is a very important concept here. So we break down the thread from grid to block and block to warps. And each time only one, not only 1 warp, I mean, each warp would be executed on 1 SM. It cannot cross SM, okay? You just randomly throw the warps into the SM, okay? And this 16 warps has to be on the same SM because 1 block needs to be run on 1 SM. This is our assumption, okay? And how to execute these 16 warps in concurrent way, this is something SM scheduler help you to do. So this is a concept of a warp divergence. Oh, yes, here. Yeah, warp divergence. Not good. Very not good. Not very good. I should say very bad, right? I should say very bad. Because if you have the 32 threads, half threads would execute this piece of code, and another half threads execute this code. They cannot run concurrently. They must wait each other, right? So that means your code would be slower by half, right? Your code is just, the performance would be just slow down by half. So this is a really bad thing. If you have a full set of instructions and your performance is only 25% of the original. So this is a very bad thing here. You don't want to reduce your kernel performance to half, right? This is a very severe problem. And in the Fermi, this is a very old architecture, and each SM has a 32 cores, and the later architecture has more. So as I mentioned, how many CUDA cores in one SM, right? 32 cores not means that the warp have 32 threads, right? So we can have more threads, we have more cores within each streaming multiprocessor, but each thread, each warp still have 32 threads, okay? So for example, I think in the new version of V100, each SM would have, for example, I remember it's more than 60 or 128 cores, right? And but we still have each warp would have 32 threads. So this 32 threads is not necessary because they only have 32 cores, right? So in a CUDA or GPU programming, you shouldn't connect the thread with the core, right? Thread is a programming concept, and the cores is a physical or the architecture concept, right? The CUDA want to hide the architecture concept for you. They just want you to think about 32 threads, no matter how they upgrade their number of the cores. So this is the general idea, okay? Now, even if we have more than 100 cores for each thread, for each warp, there are still only 32 threads. And each time you execute the 32 threads on one warp. One warp with 32 threads on one streaming multiprocessor. Okay, so you can see here, yes, I didn't pay attention to this sentence. Okay, Turing maintain 128 core standard, right? Just I mentioned, V100 is a Turing architecture. It has a 128 core standard, but it's still 32 threads per warp. Okay, so there is some parameter here. What is the maximum number of thread per block, as I mentioned, and the maximum number of the blocks per grid, and the thread per warp. This is some concept you must remember. Maximum number of the concurrent warp per SM. As I mentioned, if I use 500 threads per block, right, and then I will have 16 warps. So the maximum warps you can run concurrently with one SM is 64. Okay, there are 4 warp scheduler here, and maximum number of threads per block is 32. All right, and number of the SM is 84. Streaming multiprocessor. Okay, and this is some other examples we can talk about later in the next week. Okay, I think that's it for today. And as we have already started something with the CUDA programming, I would like to give you more time for the final project because I want everyone to finish the project by the end of this month, right? And then we can do some grading or whatever before the post the grading, final grading. Okay, so I will post the GPU programming project, even if your this project 5 is not finished, but I want to post something, right? And you can understand the requirement of our final project, and I will post the CUDA GPU code online. Okay, and if you have any question, you can stay in the meeting room. We can have some other discussion. Or if you have any question, just unmute. You can ask now. Yeah. So any question?
Yeah, I just put it in the chat, but when will projects 3 and 4 be graded?
I almost finished all the grade, and I will post the grade, the scores by the end of this week. I'm not quite sure. I received several emails from the college level or school level, but I don't know when is the time for you to decide you want to go for PNF or go the real grade. Does anyone know that?
That is April 24th.
April 24th. Okay, so before April 15, or by this week, I try my best by this week, before April 15, I would put all the project and the midterm score online, and you will have some days to decide which direction you want to go, okay?
All right, thank you.
Mm-hmm. Any other question?
Oh, I also noticed when you were doing that code demo earlier, when you were compiling all the CUDA code,
Mm-hmm.
why did you compile with a C++ and the NVCC, like the both after you compiled like both the CUDA code and the regular code?
This is a good question. So I think I understand your question. Your question asking us why finally I link with, I use a different compiler to compile, right?
Yeah.
So let's go back to this. Okay, so here, if you look at the code, I first use the NVCC to compile the CUDA code, right? This is something you must use. Otherwise, GCC cannot, or G++ cannot recognize the, I should exit to the login node. Okay, so if you are using the GCC, I don't think the compiler can help you to, right? You have to use NVCC because this is a CUDA device code, right? So you cannot use GCC or G++ to compile this CUDA code. And for the original device code, definitely you can use the GCC, right? There is nothing confused here. And finally, you just need a compiler to link all the object file together. You can use NVCC, you can use the G++, no matter, but it's safe to use NVCC to link them, right? Mm. So this is compile the object file, this is compile the host file, and this is to link the host file and the device file together, right? To generate the final executable. Okay, I'm not sure. I think let's try if I can use NVCC for me. Yeah, it's also fine. So maybe you just keep using NVCC for everything. It's also okay. I just want to demonstrate here, device code, you should use the original method. For for the host code, you can use the original method, but for the device code, you should use the NVCC, and you have something to link that together, right? But anyway, if you just to take the CC as the NVCC, you can use NVCC for every piece of the code. Is that right?
Yes, thank you.
Mm-hmm. Any other question? Okay, so if everything sounds good to you, let me try to post today's contents and the code online, and you can play with the code in your laptop if you have NVIDIA GPU, or in the cluster, or in the Alabama Supercomputing Authority cluster. Okay, and let me know if you have any question. Okay, so that's it for today. Yeah, thank you everyone. See you next week.